Welcome to Math with EJD. I've been on this series about numerical computation of eigenvalues and eigenvectors. And we have seen some of these numerical methods, okay, for computing eigenvalues and eigenvectors to be things like power method, and we have what you can call the iterative method, inverse iterative method. We have the QR method, and of course the Rayleigh quotient method. Rayleigh quotient method. In previous videos, we had dealt with power method, inverse iterative method, QR method. Now the focus turns to Rayleigh quotient method. So let's go. Rayleigh quotient method for computing eigenvalues and eigenvectors. Interestingly, the Rayleigh quotient method looks a bit like power method, and it looks like power method the the inverse iterative method, right? So let's see how that looks. The Rayleigh, the Rayleigh quotient method is an iterative technique for approximating approximating eigenvalues and eigenvectors of a symmetric matrix. Of a symmetric matrix A. Now, given an initial estimate, an initial estimate, an initial estimate, x naught, which is a non-zero vector, the method refines the eigenvalue, the eigenvalue approximation using the Rayleigh quotient. Interestingly, the Rayleigh quotient looks like what we saw for the um, power method. So the Rayleigh quotient R of X is actually XK transpose AXK all over XK transpose AK. This is actually the same thing as XK transpose uh XK plus 1 all over XK transpose. Okay, this is actually not AK now. So um XK transpose XK transpose XK XK transpose XK. Okay, so either of this would pass. So that's the Rayleigh quotient, which is just exactly what we had for the power method, and I think for inverse iterative method, except for few differences in between. So here, where xk is the normalized estimate, xk is the normalized estimate of the eigenvector at iteration k. So let's look at the algorithm. The algorithm for the Rayleigh quotient method. First, choose an initial guess, x naught, often a random non-zero vector, a random non-zero vector. Same for same for power method and inverse iterative. Then next you normalize xk at each iteration. Then three, compute the Rayleigh the Rayleigh quotient. Compute the Rayleigh quotient, which I call R of let me walk about the notation. Let me call it RK, right? Compute the Rayleigh quotient R RK. Should I call it that? Yeah. Compute the Rayleigh quotient RK, okay? So compute the Rayleigh quotient RK. So for update XK by solving A minus RKI Y equals XK. Update XK by solving that and setting XK plus 1 to be equal to Y over norm of Y. So that's where the normalization thing happens. So this may be the little difference between it and power method and inverse iterative or something like that. So 5, you have to repeat until RK converges. So this is more or less like the lambda key we were talking about before. So let's take an example. Same example all the way. Given A equals 4, 1, 2, 3, and an initial guess, and an initial guess, um, an initial guess x naught, which is 1, 1. That's the usual thing we'd take. So given this now, um, so let's go for the first iteration. So uh let's call that iteration 0. I mean, we can call it iteration 1 also, that's okay. So first of all, we normalize. Yeah, this is where this is different. So we normalize x naught, right? Which we started with. So now our x naught is equal to um the original x naught divided by the norm of that x naught. We'll still call it x naught all the way, all the same. So this is 1, 1 all over the norm of 1, 1, okay, which is 1 over square root of 1 squared plus 1 squared into 1, 1. So that means that we have that that's 1 over root 2 into 1, 1. So in essence, x naught is equal to 1 over root 2, 1 over root 2. That goes. So that's the first step there. Then the second step will be to compute the Rayleigh coefficient, compute the Rayleigh quotient, right? I wonder why I keep calling it coefficient. Compute the Rayleigh quotient. Now, you know that we are on the zeroth iteration. So R naught would be X naught transpose A X naught divided by X naught transpose X naught. Okay. So R naught now would just be X naught transpose is simply 1 over root 2, 1 over root 2, like that, into A itself, that's 4, 1, 2, 3, then into 1 over root 2, 1 over root 2, all of that, all over 1 over root 2, 1 over root 2, into 1 over root 2, 1 over root 2, like that. So we have the setup there, so we just need to dissolve all of this. Yeah, so I think I'll just walk very fast. Just getting the answers. So here we have 1 over root 2, 1 over root 2. We have that first. Then for this area now, so because we have two rows, we can write this twice. So we have 1 over root 2, 1 over root 2, 1 over root 2, 1 over root 2, like that. Then put over it 4, 1, 2, 3, 4, 1, 2, 3. Okay, so that takes care of this part. That takes care of this part. Then down here, we still, so let's still maintain this 1 over root 2, 1 over root 2 into 1 over root 2, 1 over root 2, so that now R0 is equal to, so we have 1 over root 2, 1 over root 2 into, if you can do this straight, fine. So this is 4 over root 2 plus 1 over root 2. That is 5 over root 2. Okay, if we add the two together. So this is 5 over root 2. This is 5 over root 2 all over. And so 2 times 1 over root 2 plus 3 times 1 over root 2. That's another 5 over root 2 all over 1 over root 2, 1 over root 2 into 1 over root 2, 1 over root 2. Okay, so that R0, the first Rayleigh quotient, is now, so we can do all this now. So we have 5 over root 2, 5 over root 2, then put those over. So you have 1 over root 2, 1 over root 2, all over 1 over root 2, 1 over root 2, then put over it 1 over root 2 again, 1 over root 2. So this is one value, this is another one value. So we have R naught to be equal to 5 over root 2 times 1 over root 2. That's simply 5 over 2 up there, plus another 5 over 2 down. That's 5 times 1, 5. Root 2 times root 2 is 2. Then down here we have 1 over 2 plus 1 over 2 again. 1 over root 2 times 1 over 2. 1 times 1, 1. Root 2 times root 2, 2. So R naught is equal to, for the top now, we have LCM is 2, then 5 plus 5. Or let's just say 10. Let's go for 10 straight. And down we have 2 over root 2. So finally, we have R naught to be equal to 5 all over 1. So the first Rayleigh quotient is 5. And that goes. That goes. Now that's just the beginning, right? That's the zeroth iteration. Okay. So now we now need to solve. You remember there's something to solve, right? We have to solve this expression. So we want to update xk now by solving this. We want to get xk plus 1. So um so that is the first iteration, or call it iteration 0, I or rather iteration 1, iteration 1. Okay, so So iteration one now, um, we have we have to solve a minus r, a minus r naught, the r naught we just got now, a minus r naught I multiplied by y equals x naught. Okay, so that we can get, so that we can get, instead of calling it y, instead of calling it y, do we have to call it y? Uh, it should actually be, I think it's better to call it, okay, well, xk plus 1 is going to be, so x1 is going to be when we normalize y. So that, so we are good. Okay, so now we have a is 4213, right? A is 4213. Let me be sure of that. A is 4123. 4123. 41. A is 4123 minus R naught. We already got R naught to be 5. We got R naught to be 5. So that will be 5005. So into y1, y2 equals x naught is 1, 1. That was what we started with. So in that case, we have 4 minus 5, that's minus 1. 1 minus 0 is 0. 2 minus 0 is 2. 3 minus 5 is minus 2 into y1, y2, and that is equal to 1, 1. Okay? So we can have, so because of these two rows now, we have y1, y2, y1, y2. So y1 minus 1, 0, y1, y2, 2 minus 2. If that's okay, yeah, I think it's fine. So that is now equal to 1, 1. So we have minus y1 equals 1. And then we have 2y1 minus 2y2 to be equal to 1 again. Okay. So since, so of course, we can easily solve this because this is simply that y1 equals minus 1. Y1 equals minus 1. And then, so if that is the case, we have 2 into minus 1 minus 2y2 equals 1. So minus 2 minus 2y2 equals 1. So minus 2y2, or better still, minus 2 plus 1 is equal to 2y2. Is it minus 2 plus 1? That's minus 2 minus 1. So this is minus 2 minus 1 equals 2y2. So that's minus 3 equals 2y2. So y2 is equal to minus 3 over 2. Minus 3 over 2. So what do we have? Y1 is minus 1. Therefore, y1 is minus 1 and y2 is minus 3 over 2. Okay. So in that case now we can say therefore y is equal to minus 1 minus 3 over 2. Minus 1 minus 3 over 2. So we can now normalize. So x1 now is equal to y all over norm of y. So that means we have 1 over square root of minus 1 squared plus minus 3 over 2 squared into minus 1 minus 3 over 2. Okay. So x1 is equal to y over absolute value of y, norm of y equals 1 over square root of 1 minus 1 squared is 1 plus 9 over 4 into minus 1 minus 3 over 2. That's our x1. So x1 is equal to 1 over, I mean, this is 4 over 4. That will be square root of 4 over 4. Oh, that's 13 over 2. I mean, 13 over 4 now. 13 over 4. If you add up all this into minus 1 minus 3 over 2. So x1 is equal to, I mean, because of this now, this can actually be 1 over root 13 over 2 into minus 1 minus 3 over 2. So that means that x1 is equal to 2 over root 13. You know, the 2 can go up. 2 over root 13 into minus 1 minus 3 over 2. So x1 is equal to, if you open up all of that, this is going to be minus 2 over root 13 up there. And down here, 2 cancels 2. So we have minus 3 over root 13. Okay. So with that done, we can then compute. So we can compute R2. I mean R1, that's the next Rayleigh coefficient. So we have R1 equals X1 transpose A X1 all over X1 transpose A, I mean X1 transpose X1. Okay. So that means that R1 is equal to, what is X1 already? X1 is, okay, this thing we just got, minus 2 over root 13, minus 3 over root 13, minus 2 over root 13, minus 3 over root 13 into A 4, 1, 2, 3, right? 4, 1, 2, 3. I have to be sure of that. 4, 1, 2, 3, yeah. 4, 1, 2, 3. So was I okay here? Hope I've not done anything wrong. Yeah, I think we're good. Then 2y1 minus 2y2 equals 1. Okay. So 4, 1, 2, 3 into minus 2 over root 13 minus 3 over root 13 all over minus 2 over root 13 minus 3 over root 13 into minus 2 over root 13 minus 3 over root 13, like that, so that R1 is equal to minus 2 over root 13 minus 3 over root 13 into, if we can go fast, is it possible? Okay, let me just do what I've been doing. Minus 2 over root 13 minus 3 over root 13 minus 2 over root 13 minus 3 over root 13. So this will be 4, 1, 2, 3. 4, 1, 2, 3 into minus 2 over root 13 minus 3 over root 13 into minus 2 over root 13 minus 3 over root 13. Okay, so that R1 again is equal to minus 2 over root 13 minus 3 over root 13 into, when we do this, this is minus 8 over root 13 minus 3 over root 13. Okay, minus 8 minus 3, that's minus 11 all over root 13 there. And then down here, we have minus 4 minus 9. So that's minus 13 over root 13. Hope that's correct. Minus 8 minus 3 minus 11 minus 2. I mean, minus 4 minus 9. That's minus 13 over root 13. Okay, that works. And then we have minus 2 over root 13 minus 3 over root 13 into minus 2 over root 13 minus 3 over root 13. So R1 is equal to, so we do this again, minus 11 over root 13 minus 13 over root 13. Then we put this over it. So minus 2 over root 13 minus 3 over root 13 up there. And down here we have minus 2 over root 13 over root 13 minus 3 over root 13. And over it we have minus 2 over root 13 minus 3 over root 13. So that R1 now will be equal to, so if you add up all of that, minus 11 minus 2, that's minus 22 So minus 22 minus 39. This is 1. Oops, that's minus 71, right? That's minus 71. So that's minus 71 over 13. Yep. Minus 71 over 13 divided by, for this, we have 4 plus 9. I mean, okay. All right. Yeah, I think we're good. Yeah, that's fine. So, but here now, I think there's a bit of difference. So this is just going to be 71. This is just going to be 71 over 13 up there because minus minus is plus when we multiply minus together. That's 22 plus 39, which is 7. 22 plus 39 is 61. Yeah, 61. That's 61 over 13. I think that's okay now. So this is not okay. Minus minus plus. So 22 plus 39, that's 61. And down here we have 2 minus 2 minus 2, that's 4 plus 9, 13. So this will be 13. This will be 13 over 13. So that means that R1 is equal to 61 over 13 divided by 13 over 13. That's times. Okay, I mean, that would just be 1, right? Yeah, it's just because this is simply 1. So we have 61 over 13. That's R1 is roughly 61 over 13. 61 over 13 is, let me see, that's roughly 5 because 13 times 5 is 65. So that's 61 over 13. 61 divided by 13, and that is 4.69. So R1 is 4.69. Okay. So what I mean, if we stop on these two iterations, now what we are simply saying is that therefore the eigenvalue is lambda, which is approximately 4.69. Of course, we got it the first time because it's exactly 5, right? But in case I'm just trying to simulate an ideal scenario where you have to keep going, okay? That's why I've been doing all the steps all along. So what would the eigenvector be now? The eigenvector would just be okay, are we interested in the eigenvector in this case? The eigenvector is the last is the x1, okay? The eigenvector will be x1. So where's x1? X1 is where is it? The x1 we got before we got here. Yes, this will be the eigenvector now. So the eigenvalue is 4.69. Okay, let me say after two iterations, right? Okay, the eigenvalue is 4 point lambda is approximately 4.69 after two iterations, and the eigenvector the eigenvector is um minus 2 over root 13 minus 3 over root 13. Now, because this it may have a matrix that is really complicated, it is important to understand how the uh, Python code looks like. So this is what the Python code looks like. We define the Rayleigh coefficients in the Rayleigh quotient in verses, I mean, lines 4 and 5. And then the method is also defined in 8, 9, and 10 and all that. I mean, just like you saw already, we know the eigenvector, the dominant eigenvalue of this matrix is 5. So after first iteration, we already got the answer, if you remember. So, but for the sake to just understand the code, I just wrote all this. So this just takes only one iteration and then we get 5.0. Although our eigenvectors are different, but okay, the first eigenvector, let's see, that first time. Okay, I mean, this is what the Python code says. So you find it on Facebook. You find it in the caption. I'm not able to put it on YouTube because of the square brackets that are necessary for in this code. Okay. So find it on Facebook. You can just copy it and check it out and tweak it and see what happens. Okay. So you will see that we already got our five straight after the first iteration. Okay. We already got five. So the first Rayleigh coefficient R naught is 5. So and the corresponding eigenvector is 1 over root 2, 1 over root 2 from first iteration. We already have that. So of course, 1 over root 2 is actually 0.7071, and that's what you see for the from the Python part of things. So just one iteration, we already have the answer. But I just did the second iteration to explain the process. So 0.7071 is actually 1 over square root of 2. Then the eigenvalue is already 5. Okay, so that works. All right, so with that, we come to the end of the Rayleigh quotient method for computing eigenvalues and eigenvectors. If you have subscribed to the channel, thank you so much for that. If you have not, you'll be missing a lot if you do not. So go ahead, hit the subscribe button and hit the notification bell also so you can always get alerted each time a new video is released. Then comment, let me know how helpful these videos are for you. Let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. And don't forget to like and share so that more people can have access to this great learning. Till I come your way again, keep doing maths right. Bye.